Okay, right now, if you go here to events, there is an icon here that allows you to simulate. There is an icon over there at the top that allows you to access the events. Okay, if you click there, you can see here. This is the short circuit event that you already defined. And also, if you want to edit, you just double click here and you can see this is the event that you create. This is the short circuit event. The time is 0, 0, 0. That means 0 seconds. You can see over here 0 seconds. And the object that we are applying, the short circuit, is the HV bus bar, this bus bar over here. Okay, and here we are defining a three-phase short circuit on the bus bar HV, and the resistance and the reactance, they are 0. Okay, let's close here. Okay, first step done. First step, define the disturbance. That is done, no problem. Next step. The next step is I would like to show you some numerical results. I want to show you some numerical results from the time domain simulation. As I say in my videos, because you know I spend hours talking in the videos, as I say in my videos, Power Factory has thousands of variables that you can plot, that you can use for your assessment, for your coursework, for your projects. Okay, there are many variables, and those variables, they are extremely useful. But because there are thousands of variables, and when you solve the time domain simulation, those variables require memory space. Power Factory is allowing the user to define the variables that they want to assess. If you follow my cursor, my pointer here, there is an icon that is extremely important at the top. And that very specific icon is extremely important because over there, if you click, that icon is the one that allows you to see the result variables that we have. Okay, you can see over here variable selection, and at this moment there is nothing here because Power Factory by default is not having any variable included in the memory. For that reason, you must define by yourself the variables that you want to explore, or later the variables that you want to plot. For that reason, close here, press close here. And again, because my student complained that I spend so many hours in the videos, what I will do is the following. Okay, I will use the basic method. I can spend here more time explaining more details and so on, but my student want the short version. Okay, right button, I select the generator. Okay, I select the generator with a single click. Then I select the right button, click, and then you have the possibility of going here, define, and result for simulations RMS. Okay, as you can see over there, it's extremely simple. What I am doing is basically right button on the generator, then results for simulation RMS. Okay, if you click over there, what you can see is that Power Factory automatically is creating a object result. Okay, now we can see here in the object result, the name of this object is G, because that is the name of this synchronous generator over here. Okay, that is the object. And if we double click, I'm sorry, let me do it again because my student can complain. If we double click here, what is the interesting thing? That Power Factory is by default giving you a number of select variables. Power Factory is making your life easy because there are few variables here that they are already defined and ready for you. For instance, the power turbine, the terminal voltage, the excitation current, positive sequence active power, positive sequence reactive power, current, blah, 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 etc. Of course, because my students, they only want the short version. They must read the technical documentation and they must understand the meaning of every single of those variables, okay? Good. Let me close here. And now I will do something similar, okay? Right button, define RMS results. Done. Now we have an object for results coming from this transformer, okay? And you can see again, there are some predefined data here, okay? Power Factory already make your life easy and include some results over there. Then let me do the same here at the transmission line. Right button, define RMS, and we have results for line number 1. And now let me do the same. Let me define results for AMT RMS, okay? Line number 2. Finally, there is only one thing missing, and the only thing that is missing is that the only thing that I need to have a look over here is the external grid, okay? Right now in the external grid, I will do define, okay? Define, and again, result simulations. And right now you can see here G, the infinity bus bar, line 1, line 2, line 3, okay? Again, those names that you look over here, they are connected with network objects, okay? Network objects. And inside every single of those, they are result variables, okay? I will repeat again. We can go here, and here you can see the list of objects that we are collecting data. Those names, of course, they are connected with every single network component here, and they are connected with those components over here. And if you double click one of them, of course, there are many variables, okay? There are many variables already predefined by Power Factory, okay? Okay, close. Now we are almost ready to run a simulation here, okay? We are almost ready to run a simulation, okay? And the simulation is extremely simple. What we will do is the following. Again, remember, initial conditions. Let me clear here the output window, okay? Because I want my students to see everything here. Oh, Jesus, this cursor is killing me. This pointer is killing me. Okay, let me run initial conditions. And as you can see over here, everything is fine. Power Factory is telling you that there is a reference bus bar, okay? The nominal frequency is 50 Hertz. We already know that. And then Power Factory say initial conditions calculated, okay? Something very interesting that you can see over here, the time is minus 100 milliseconds, okay? Well, we don't have time to explain that here. You can read more on the user manual, because then the student complained that I am spending so much time. But let me start here the simulation, okay? The next step is press here the button, okay? And we need to define the time that we will use to run the simulation, okay? Okay, let me reduce here. Let me put here 5 seconds, okay? Let me use 5 seconds. In a minute, I will reduce this number, but let me use 5 seconds, okay? And right now you can press here, execute, okay? I will do it again, okay? You select here the command simulation. You select here the time, I say 5 seconds. And now I will press execute. Ta-da! Something that is very important for you, okay? Something that is extremely, extremely important for you. Power Factory has run the simulation. Every time that you run a simulation, please go to the output window and read those messages, okay? Because Power Factory is talking to you. Here you can see at t equals 0 milliseconds, a short circuit is inserted, okay? And the interesting thing is, look over here, there is a small lightning symbol over here, and this small lightning symbol is representing the short circuit happening in the H bus bar, okay? And of course, because this is a solid or voltage short circuit, you can see that the voltage is 0, okay? But coming back here to my explanation, you can see 0 is the starting point of the short circuit. And then here, Power Factory tells you, something is happening. At 1.072 seconds, generator out of step or pole sleep, okay? And this is extremely important because Power Factory is telling you something extremely, extremely important. The first one is Power Factory is telling you that the synchronous machine is out the step. Out the step is losing the synchronism. I mean, Power Factory is making your life easy here, and Power Factory is telling you that if you are assessing the rotor angle stability, Power Factory is already telling you that this system is unstable. This system is unstable because the synchronous machine is losing the synchronism, okay? Another name for losing the synchronism, there are several synonyms, okay? There are several terms that they can be used for indicating loss of synchronism. Out the step is one of the phrases. Pole sleep is another phrase. But again, Power Factory is telling you that this system already is not stable, rotor angle stable, okay? And finally, the last comment over here is that Power Factory is telling you that the simulation was executed, successfully executed, and that was at 5 seconds, okay? Okay. This is the first part. Now let me do the following. Now what I want to do is I would like to see the plots. I want to see the time domain response, because the time domain response is the only way that you can have a proper understanding about the phenomenon, okay? For that reason, let me do the following, okay? What I will do right now is you can see the big pointer over there, okay? And I unfroze the diagram, okay? I unfroze the diagram, and what I will do is now you can follow the cursor, okay? You can follow the indicator, and there is a plus or positive sign at the very top. And over there you can see that we can for instance press over there to create a new graphic object. And this new graphic object is basically the option that allow you to create graphic object for representing time domain plots, okay? For that reason, I will select here the option for plot page. I will put the name over there, plot. Let me use plot and then results, okay? Because right now what I will do is plotting the results, okay? Be careful, select this option here, plot page. If you select another of those options, I'm not responsible for that, okay? You must select plot page and then execute. And right now, Power Factory create what we call a virtual instrument. A virtual instrument you can imagine like a white paper. And that white paper can be used for including more graphical objects. And the graphical objects that we are talking about, we are referring to the plots, okay? We are referring to the plots. In this case, what I will do is the following. I will include here a couple plots because we are interested, remember, we are interested on rotor angle stability. If we are interested in rotor angle stability, well, there are two very important variables, electromechanical variables that we need to care of. And one of them is the rotor speed and the other one is the rotor angle, okay? What I will do is the following. Follow the big icon over here, the big cursor, and there is an icon on the top left hand side. You can see over there that say insert plot, okay? I repeat again, here at the top right, you can see that there is an icon over there, and that icon is to insert a plot. What I will do right now is click, and right now Power Factory open a dialog window for you where you can select the type of plot that you want to do, okay? If you are a rookie user, well, I highly suggest that you go here to Simulation RMS, and Power Factory is filtering for you the plots here, okay? Because depending on the study that you are running, Power Factory have many different plots, okay? If you are using quasi-dynamic simulation, there are some plots. If you are using modal analysis, there is another plot. If you are using probabilistic analysis, there are some other plots. And here we are running RMS, okay? It's the first option. And I will select here the classical plot, okay? This is the classical plot. What you need to do is select and then say, okay. When you select OK, Power Factory will come back to you and say, okay, you want to create a classical plot. And now Power Factory is asking, okay, I need to connect this graphical object with some numerical data. This graphic object must have the name and the object name and the variable that you want to plot. For that reason, if you click here, element, and I will select the generator, okay? Because we are here working on rotor angle stability. I will select here the generator, ta-da! And right now you can see here the element is the synchronous generator. And now, by default, Power Factory is making your life easy. If you click here, you have options. You have the option to select the variable that you want to plot, okay? Of course, those variables, they are stored in memory because we already defined the result object, okay? In this first plot, I will do something very simple. I will select here the rotor speed. Of course, I know that this is the rotor speed because I already read the technical reference. But here you can select here rotor speed, okay? And right now you can see that I complete the data. We have here the generator. We have here the variable rotor speed, at speed. And then I will say, okay. Wow. Look over there. Brilliant. Lovely. I love this. This plot, I believe all of you can see here at the very bottom, the name of the variable that we are using here. This is the generator speed. And as you can see, before zero, there is no disturbance. The power system is in a steady state, okay? Let me see the value. What is the value before we have here the here. Yes, here we have a value of 1 per unit, okay? Here you can see we have 1 per unit. And let me check the value. You can see T equals minus 0.04. And you can see here the value 1 per unit. Beautiful. We are in time below 0. And as consequence, you can see the machine is in a steady state. But in T equals 0, the short circuit happened. And as you can see, look over here how the rotational speed increase. You can see here after 5 seconds, after 5 seconds, the rotor speed reached 1.16 per unit, okay? Okay, but this is the rotor speed. And when we are working with rotor angle stability, we need to care is about rotor angle. And to include the plot for the rotor angle, now let me show you. We will go here again to the same button over there, okay? On the top left hand side. Top left hand side, you can see there is an icon over there. You can click, and I will select again RMS simulation, and I will select here curve plot, okay? With the curve plot, I will select okay, and power factor is asking me again. Please tell me what is the object that you want to plot the variable. And I will click here, click. Now select the generator, beautiful. And now I will click here and I will select this variable. This is a calculated variable, feed rail. I already know that is the variable that I need to plot, but my student, they need to read technical reference. Go to the technical reference of the synchronous machine, and you must understand this is the rotor angle in degrees. This is a calculation variable. And now I will say okay. Wow, this is amazing. This is amazing. I don't know if you realize, okay? I don't know if you realize, but what is happening in this plot? Well, this plot is amazing. Because this plot is telling me that before the contingency, okay? We have a rotor angle that we already calculated, okay? Remember that we already calculated this angle. We calculate this angle and it was 13.21 degree. And that is the internal rotor angle in this machine. We are using the most simple model for this machine. We are using the constant voltage behind the reactance, okay? However, all my students, they are extremely clever. They took the previous semester, they took a class about power system, and they understand clearly the model of the synchronous machine. But coming back to my explanation, you can see over here, this is the initial rotor angle, and everything is fine. But the problem is that when we have the short circuit at t equals 0, the short circuit is inserted. And as you can see over here, the rotor speed start to increase. And you must remember from the theory, because of course those videos that I spend hours making for you, those videos, they explain theory. But the short history here is because we have mechanical power and we don't have electrical power, because the short circuit is happening here. If the short circuit is happening here, there is not active power going to the infinity bus bar. And as consequent, there is not electrical power to stop the acceleration of this machine. We have pure mechanical power accelerating this machine. And as the mechanical power is accelerating the machine, the rotor is increasing the speed. But because the rotor is increasing the speed, you can see how the angle is increasing. You can see over here. Let me follow here, okay? You can see here how the angle, look over here, 19, then 23, then 46, then 124. Oh my goodness. And then reach here, look this number, 178 degree. And that is 0.72. And then, I don't know if you can see, but here there is a jump. This jump is coming from 180 positive, look over here, minus 180, roughly. What is happening there is that Power Factory is creating a plot where the rotor angle is defined between 180 degrees and minus 180 degrees. What I'm telling you is that this rotor angle is taking off. But Power Factory limit the plot between 180 positive and minus 180. And that is the reason that you have these like, I don't know, very ugly eyes. No, very ugly teeth. Let's say that. What I'm telling you is that this jump from here to here is because the angle overreach 180 degrees, okay? But this is quite interesting because when we see this behavior like this, the system is not stable, okay? In this case, the system is not stable. Rotor angle stable, okay? You can see over here the rotational speed increase, and the rotor angle start to increase, but after 1 second, 1.0072 seconds, this machine lose the synchronism, okay? Okay, now the interesting question is why this is happening. Why this system is unstable. And to be honest, this is not so complicated. If you know theory, you know equations, you can explain this. And the situation is extremely simple, okay? You have this system working in a steady state. You have a short circuit here. When the short circuit is here, of course, you have zero voltage. And there is no way that this machine produces active power that can be delivered here. And that consequence, all the mechanical power that is applied here is converted into acceleration. And that is what is explaining this sudden increase in the rotor speed, okay? A very interesting question for home for my student is, please calculate at home the slope of that rotational speed, okay? It's a very tricky and very interesting question, and because we are running out of time, please for home calculate the slope of this curve, of this plot, because you can see this is almost a straight line, okay? This is a straight line, and every single straight line there is a slope. Calculate the slope, and then we can conclude, okay? Second very important thing here is this angle is increasing, and because this angle is increasing, there is a moment where we can identify there is a pole slip or loss of synchronism. Now, the interesting question here is, okay, professor, how do we solve this situation? Okay, This situation is really bad for the power system because we install this short circuit, we insert this short circuit, but that short circuit stays over there. And because the short circuit stays over there, the machine has no possibility of recovering from the massive acceleration that is happening during the short circuit. What I will do is the following. Let's assume that that short circuit is inserted at t equal 0, okay? Let's assume that this short circuit is inserted at t equals 0. But now what I will do is, after few cycles, after few milliseconds, I will remove the short circuit. I will clear the short circuit. I will repeat again. We assume that the short circuit is happening at t equals 0, okay? You can see that here, okay? You can see here that we are inserting the short circuit in t equals 0. But right now, let me clear that short circuit. I will clear that short circuit. I will clear that short circuit after 100 milliseconds, okay? Let me do that. Power Factory allow me to define as many events as I want. The short circuit that we include here, that is an event. But in order to remove that event, I need to have another event clearing the short circuit. And that is my job now, okay? What I will do now is run initial conditions. I will go here to this bus bar, right button, okay? And I will say define, look over here, define a short circuit event. Probably my students are puzzled or they are confused now. Why another short circuit? Because the name of the object is short circuit event, okay? The name of this object is short circuit event. And select that, okay? Now, we want to clear the short circuit in 100 milliseconds. And to clear the short circuit in 100 milliseconds, what I will do is, I will include here in time 0.100, okay? If you look over here, I am defining a new short circuit event. And this event is happening at 0.1 seconds or 100 milliseconds, okay? The event is happening on the same bus bar that we previously installed the short circuit. But now what I will do is select here, there is an option, clear short circuit. Again, I will tell you, here I will select the default type is clear short circuit, okay? I select here clear short circuit, and right now we have two events. One event that occur at t equals 0, that is the short circuit, okay? And the second event, let me go back here to events. The first event is the short circuit, and the second event is clear the short circuit, okay? Before somebody start to make me question, how do you change the name? Double click, okay? This is like normal Windows, okay? You double click here and you can change the name, and I include in the name clear short circuit, okay? Right now we have two events. First event, short circuit at t equals 0. And then 100 milliseconds later, we have here the clear short circuit. Okay? Nice. And let me do the following. Oh, Jesus. Okay, here. Yeah. Let me clear the output window. Clear the output window. Yes. Okay, we clear here the output window, okay? Now, let me run initial conditions. Beautiful. Power factory is telling me we have an infinity bus bar. That is the reference. We are using a system that is 50 Hertz, perfectly fine. And then we have here initial conditions. Fine. Next step, let's go here and run the simulation. Again, we are running 5 seconds. I think this is too much, but let's use 5 seconds. I will not change anything here, okay? I will not change anything else. Now let's execute. Oh, wow, what is happening here? Look over here. Power factory is telling me the following. Power factory is telling me that at t equals 0, the fault is inserted. And this is a short circuit. Over here you can read, it's clear. It's a short circuit, fault impedance 0 and 0. And then we have at t equal 100 milliseconds, I love using milliseconds, at 100 milliseconds, the fault is, the short circuit is clear, okay? And that is perfectly nice, I love it. And then there is a message here, there is an information that say the simulation was successfully executed at t equal 5 seconds, okay? Nice, beautiful. Okay, right now what I need to do is I will go here to plot results. Oh, look over here. This is amazing, okay? Now what I will do, no, this image is so small, okay? I want to use those buttons over here, okay? Be familiar. You can go to the user manual, okay? Because my students say that I spend so much time on those videos. But there is a button here to auto size the horizontal axis and then the vertical. Oh, wow, look over here. Now you can see something beautiful. You can see something beautiful. This is the rotor speed. This is the rotor speed, okay? You can see here the rotor speed. Sorry, here the rotor speed. And here you can see the rotor angle. Beautiful. I love it. I love it, but there's something here that probably you are not so aware, okay? I will explain a bit more in a minute, okay? But here you can see the following. I don't know if you realize, let me zoom in here. But I don't know if you realize, but the machine is still accelerating like a straight line. The machine is still accelerating. During the short circuit, you can see this is, let me use my my big pointer, okay? You can see over here, the machine, this is the rotational speed. The rotational speed starts from the synchronous speed, 1.0 per unit, and the machine starts to speed up, speed up, speed up, speed up, speed up. Oh. And here, this is the moment where the short circuit is clear. When you disconnect the short circuit, now the machine has the possibility to deliver in active power to the network. And that is the moment that the machine tries to reach stability. That is the moment where the rotor tries to regain an equilibrium point and to reach stability. And coming to the angle, you can see this is the original angle. And the angle takes off because the machine is accelerating. The machine is accelerating, and as consequence, you can see here, the machine is accelerating. But at the moment that the machine is accelerating, this is the starting point, okay? This is the starting point. The machine starts to accelerate. You can see how the angle is increasing, 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 increasing. And suddenly we reach here the point 100 milliseconds where we clear the short circuit. And that is a very important point. Because when we clear the short circuit, okay, the rotor speed oscillate and try to regain a equilibrium point. And the rotor angle, you can see the short circuit is clear here, but the rotor angle keep increasing. But that was because the inertia of this machine stores so much energy. In this process from here from t equals 0 to t equals 100 milliseconds, in this period, the machine accelerates so much that it stores so much energy, kinetic energy. The rotor is full of kinetic energy. As a consequence, the rotor angle increase, and even when we stop the short circuit, we clear the short circuit, the rotor angle is still opening, but reach this maximum here. And then you have several oscillations, until the machine reach the steady state. What is the bad news? The bad news, my dear student, is that we are using the classical model for this synchronous machine. And in this model, because we are using a pure reactive power system, there is no resistance that they can dissipate the energy. And because they are not resistance in this system, there is no damping helping to reduce those oscillations. And that is the reason. Let me run the simulation by, let me say, 60 seconds. If we run the simulation by 60 seconds, you can see that after 60 seconds, the oscillation start to decrease. And if we run this simulation, let's say 120 seconds, you can see now that the oscillation, the rotor speed oscillation, is increasing in amplitude, and here the rotor angle is decreasing in amplitude. And that is amazing, because right now I can demonstrate to my students. Let me run, because probably one student will say, I don't see that. Okay, let me run this 300 seconds. If we run this 300 seconds, I believe that now you can see that the rotor angle, the rotor speed is coming back to 1 per unit. I believe my students can be convinced of that. And also, my students can be convinced that the rotor angle is reaching a very specific point, and in this case is reaching around 13.2. And that was the original, similar to the original rotor angle. If you remember, the original rotor angle, it was 13.21, and here after 300 seconds, this system is reaching again stability, is trying to reach a steady state point, and that is happening at 13.2 degrees. Yeah? Okay, this is beautiful. I love these kind of plots because you can see the oscillations, and also you can see after 300 seconds it's clear that this system is fully stable. Okay, I believe you must understand this system is full stable. This system is totally stable. Okay, good. Something that I want to do, I know my students, they say, okay, but in classes you use a video and you talk about equal area criteria. Can we use the equal area criterion in Power Factory? Power Factory cannot do the equal area criterion, okay? We cannot do that because Power Factory is a time domain software. It's a software created for running time domain simulations, and then from the time domain simulations, the user can conclude about the rotor angle stability. However, something that I love to do for my students is I want to show you something quite interesting, okay? What I will do now is, again, let me run initial conditions, okay? As usual. Run initial conditions, everything is reset to 0, okay? I'm sorry. What I will do next is I will go back here, and there is a button that say insert plot, okay? What I will do now is insert a plot. And what I will do now is I will show you here in this, no, sorry. Let me go back again. Initial conditions, and I will create a new virtual instrument, okay? New virtual instrument is extremely simple because this is similar to Excel, Microsoft Excel. You can go here to the top, press the positive sign, and Power Factory will tell you, okay, what kind of new graphic object you want. And I will tell, okay, I want again a plot page, okay? And I will call this plot result 2. Okay, right now we have a name. Here we have the selection, the new object. It will be a plot page. And we have here a empty page, okay? We have a graphic object ready for your plots. The first plot that I want to show you, is, let me select here plot and go to RMS, RMS and AMT, and then here curve plot, okay? Now Power Factory is asking me, okay, you want to create a plot. Please let me know what is the object element that you want to show. And I will select here the generator. Perfectly fine, done. Next step, I will select the variable, okay? The variable that I want to show you at this very moment, is the electrical power, okay? I will select PGT. PGT is the name of the variable. It's a signal inside the Power Factory. However, my students, they will go to the technical reference of the synchronous machine. They will read that, okay? And what I want to do now is press OK here. And what I will do is run the simulation. But instead of 300 seconds, we were running 300 seconds because I was showing you the steady state point, okay? But let me run again 5 seconds. Oh, wow, what is this? Look over here. What is happening here? What is happening here is this is the plot of the positive sequence active power at the terminals of the synchronous generator. In other words, what I am showing you is the active power that is coming out from this synchronous generator here, okay? That is what I am showing you in this result plot here. This is the active power. Before the short circuit happened, we have an electrical power of 0.75. No, this is not electrical power. This is PGT. This is the electrical power. Okay, it's per unit values. Come on, guys. Okay. Let me show you in megawatts because I want to make clear for my students in megawatts, okay? Run initial conditions. Let me go here to result variables, okay? I will go to result variables. Then let me go here into the object that is pointing to the synchronous generator. Double click. And I want to show you, here is megawatts, okay? Megawatts. Again, very simple process, okay? I want to show you the electrical power, but not per unit. I want to show you in megawatts. I run initial conditions, simple. Then I go here to this object here, okay? The result object, I select the result object, double click at the generator, and then select active power P. But this active power, I believe you can see that is defined in megawatts, okay? This is the one that I want to show you, okay? And remember the name because I will need this for the plot, okay? Now I will close here, close there, run the simulation, And then I want to plot is the active power in megawatts, okay? That is the one that I want to show you. Yeah, this is the one that I want to show you, and my students will be happy, hopefully, because right now we can see in a proper way that the initial power, I believe you can see here, the initial power before the disturbance, it's 60 megawatts, okay? Before the fault, the active power is 60 megawatts. But at t equals 0, the fault is happening. And look over here, how much is the power here? Oh, I told you 0. During the short circuit, because this is a voltage short circuit, because this short circuit is happening in the bus bar, there is no possibility of delivering active power. And that is the reason that the power goes from 60 to 0 and stay in 0 during the short circuit. But suddenly, after the short circuit is clear, you can see how the machine tried to recover. The machine tried to recover the steady state behavior. In this case, if I run 300-second simulation, now you can see it's very easy for my students to see that after the disturbance, you can see 300 seconds later is approaching to 60 megawatts. This system is fully stable. This system is completely stable in terms of rotor angle stability. And the good news, this system is so good that the initial steady state point is equal to the final state. That is amazing. That is amazing. To be honest, that is not happening in real life in any power system. In any power system, when you have a disturbance, the final state, if the system is stable, the final state doesn't necessarily match the initial state, okay? But yes, this plot is amazing, okay? This plot is amazing. Let me come back to my 5 seconds. Let me go back to my 5-second simulation, right? Yes, beautiful. Okay, done. I will add one more plot. The other plot that I want to add is a curve plot. I will keep working with the generator, and then I will plot the rotor angle, okay? Okay, probably you are wondering, Professor, why you are plotting P and delta? Come on, my students, you must know. P and delta, they are the most important relationship in your power system. For transient stability, for rotor angle stability, P delta curve is the most important curve, because there are many justifications and reasons, okay? But one of the important reasons is that P delta defines the non-linearity relationship inside the transient stability, and that is a very important aspect, okay? What I will do now is a final plot here. I will add one more plot, but right now I will add a very different plot, okay? The plot that I want to add right now is a XY curve plot. I will tell you again. I will add a XY curve plot. Probably you are wondering why this guy is trying to do this. Okay, give me a second and you will see. Press OK. Now Power Factory is asking what is the name of the element that I want to plot in the y-axis. And I will say my synchronous generator. Okay? What is the variable that I want in the y-axis? I want the active power in megawatts. What is the element on the x-axis? I want the generator. And what is the variable? Of course, the angle. The angle. And voila! Ooh, What is this? This is amazing. This is amazing. Why this is amazing? Let me put this one here. Okay, no, I want this on the top. And I want this in, let me use blue color. And I want, this is the rotor angle, okay? And this is the power. Let me use another color. Let me use this ridiculous number 7, yeah? Okay, what is this? Come on, my students, you must be so excited. This is beautiful. This is beautiful. Because here, this plot that I put here, that is the P delta curve. And the P delta curve, you must remember from the equal area criteria. If you remember the equal area criteria, we have a point here. Do you know who is this point over here? This point over here. I love this point, okay? I love this point. Because this point over here, this one is the initial state. That is the initial state. Yes, it is. The initial state is 60 megawatts. And the rotor angle is the rotor angle is 13.2 degrees. This is the original point. This is the original point. Then we have the short circuit. When we have the short circuit, the P goes to 0. Look over here. We have the short circuit and P is going to 0 and P reach 0. And P stay in 0 during the short circuit. But during the short circuit, look over here how the angle is accelerating. The angle is opening. The angle is growing. That is this region over here. This region over here is the active power is 0. You can see 0. The active power is 0. And the angle is opening. It's starting from here. Look over here. This is the starting point, 13 point something. You can see that is this point. And then when the short circuit is released, the short circuit is released at 100 milliseconds, yes? But when the short circuit is released, look the active power. The active power starts to oscillate. And let me show you something amazing. I want to show you this because this is beautiful, okay? This is beautiful. Here you can see the maximum oscillation. Come on. Okay, the maximum oscillation here is 102 megawatts. And here, the minimum oscillation here, let's go, yes, 16 megawatts. Look over here, let me show you, this is beautiful, this is beautiful. This point over here, 16.3, oh, and this point over there, look over here, the point, the point is 102. And if we go to the angle, that is also amazing because you can see here the maximum angle. Oh my goodness, this is amazing. You can see here the angle, rotor angle, 23, and the minimum value of the rotor angle is around here. And let me select here. Oh, Jesus, 3 degrees. Wow, my students, I don't know you, but this is amazing. This is lovely. You can see the full, this is P delta. This is P delta. And P delta, the P delta that I showed many times during those boring videos that you don't like, those amazing points over there, they are representing the P delta curve. To be honest, I cannot see something better than this. I cannot explain something more beautiful than this. Here you can see this system is rotor angle stable. You can see how the active power is changing. You can see the P delta curve. I mean, this is amazing. This is totally amazing, okay? Okay, I highly suggest that you at home you can keep exploring, because Power Factory offers you so many variables that you can explore. You can plot the current, you can plot voltages, and that is time to start to learn. Okay, this is time to start to learn. If you allow me, let me do the following. Okay, let me come back here to the time domain simulation, initial conditions, and I will run the simulation. I will run the simulation during 5 seconds. Okay, 5 seconds, and this system is fully stable. Okay, you can see the system is fully stable. Okay. Wow, this is 2 hours. No, this is too long. My student will complain, you know. Okay, I want to show you something interesting, but are you interested to learn something useful? I don't know, because people, you know, time. Well, I care about time. Useful time, of course. Okay. I will show you something that this video will be extremely watching YouTube. Okay, I will teach you something that is not out there. Okay, I will show you something that is not out there, and from there I will give you a very important concept. Okay, it's not in YouTube for sure. Okay, let's do the following. Initial conditions. Okay, initial conditions. Great. I would like to show you a very important tool that is included in Power Factory and not much people use it. Okay, this is something that not much people use it. Here there is a button. Okay, and I believe you can see that it's like a zoom with a curve inside. That is what we call the simulation scan. Okay, Power Factory allows you to indicate or to define some indicators that you can control the simulation. Okay, what I will do is I will show you this very important tool. Okay, click over there. If you click over there, there is nothing. There is nothing because the simulation scan is totally empty. At this moment, the simulation scan is totally empty. But we will create a simulation scan. Okay, to create the simulation scan is extremely simple. You go over there, you say a new object, and select new object. Okay, and Power Factory will open for you this amazing window that allows you to select some kind of objects. Okay, and I will go here, and I believe you can see there is one that is called loss of synchronism scan mode. This is a tool that Power Factory created if you don't know so much about power system stability. Okay, if you select over there lot of synchronism scan, okay, if you do this and then okay, Power Factory will create an object that is scanning one internal variable that is called outstep. Power Factory internally has a variable that is a binary variable. If the machine is stable, they use 0. And if the machine change from 0 to 1, is because the machine lost the synchronism. And that is a very interesting and useful variable. Okay, there are several options that we can run here. We can say action, stop the simulation, trip the synchronous machine, trigger, blah, 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 blah. To be honest, what I will do is the following. I will say to Power Factory, stop the simulation if the machine loses the synchronism. And we are talking about losing the synchronism, that is that the system become unstable in terms of rotor angle. Okay, that is what we are talking here. Okay, what I will do now is I will press here OK, and you have your new scan. Okay, in this case you create your simulation scan and it's there. Okay, now let me close here. Now I will tell you something. Again, it's not in YouTube. Probably this video will go viral on internet. Let me go here on initial conditions, okay? If you press the button of initial conditions, you will realize that there is an option here. In the initial condition menu, you will see that there is an option that says simulation scan. Press simulation scan. When you press simulation scan, you can see by default is not active. The simulation scan is not active by default. You need to click here and automatically will make the connection with the scan that we already defined, okay? What I'm telling you is that it's not defined, but it's right now active, okay? And in this case, when we click here, active, that is all what we need at this moment, okay? Let's say execute, nothing happened. Let me run the simulation, nothing happened. Why nothing happened here? Well, nothing happened because this system is stable. Because the short circuit, if you remember, let me run here initial conditions, and I will show you the short circuit. The short circuit is clear at 100 milliseconds, okay? What's happened if we clear this short circuit at 500 milliseconds? Well, let's clear the short circuit at 500 milliseconds and see what's happened. And Power Factory is telling me that the system is stable. Let me run the simulation by 1 second. Clear the short circuit in 1 second. Oh, the simulation stopped. Oh, the simulation stopped. Yes, of course. Because you activate the simulation scan, and the simulation scan is talking to you. Keep open, always keep open here the output window, because Power Factory will be talking to you. And if you look over here, Power Factory is talking to you and saying, I stopped the simulation, my fault, I am responsible, because at 1.072 seconds, Power Factory say, this is unstable, okay? This is rotor unstable, and Power Factory stop the simulation, okay? Now it's clear for you. Let me do the following. Now you can see that enabling this amazing tool over here is stopping the simulation for you and telling you the system is unstable, the system lose the synchronism, the machine lose the synchronism. However, we are taking so much time, so many students will complain, you know, now is the time you can complain. And here what I will do is the following, okay? Run initial conditions, yeah? We run initial conditions. Now there is something that is extremely important when we are working with rotor angle stability. There is a minimum time. I will say this slowly, but I hope my students have the ears open and the mind totally wide open. There is a moment, the maximum moment, that we can support the fault inside the power system before the system lost the stability. I will repeat again. There is a moment, there is a time from where if we clear the fault before the system is stable, and if we clear the fault after that, the system is unstable. That very specific moment is a very specific moment that receives the name critical clearing time, okay? This is the name critical clearing time. What I will try to do here in just few simulation is try to define that moment, okay? I will run initial conditions and Right now, the simulation is happening at, the short circuit is happening and clearing at 1 second, okay? What's happening if we clear at 0.99? Okay, let's see. System unstable, okay? What's happening if we clear the fault before? Let's say 800 milliseconds. 800 milliseconds, let's clear the fault. The system is unstable. Okay, let me try again. Let me run and clear the fault at 700 milliseconds. Now I run the simulation, 700 milliseconds, the system is unstable. Now, let me clear the fault at 600 milliseconds. I am reducing the time, okay? Right now we are in 600 milliseconds. The system stay unstable. Let's go for 500 milliseconds, okay? 500 milliseconds. 500 milliseconds. I run my simulation right now and... oh! The system is stable at 500. Look over here. The simulation was no stop. The system is stable. In this condition, the system is stable. Okay. Let me try 550 milliseconds. Let me try 550 milliseconds. And right now, let me run the simulation. Oh, the system stay stable. I didn't receive any message here. Okay, probably the time is a bit longer. Let me try 560 milliseconds. Oh, 560 is unstable. That means that the critical clearing time should be lower. Okay, this number is so high. Now let me try 558 milliseconds. Let me try 550 milliseconds. Unstable. Okay. Now let me try a bit lower. 557 milliseconds. 550 milliseconds. The system is unstable. Come on. I need to find this time because my students, they will complain that I am spending so much time. 556 milliseconds. Now, let me clear the fault at 550. Okay, we are in business. We are in business, my dear students. Look over here. If I insert a three-phase short circuit at t equals 0, and then I clear the short circuit at 0.556 milliseconds. Look over here. Let me run the simulation. The system is stable. You can see over here, the system is stable. Of course, the angle is oscillating, it's very ugly, I don't like it, but the system is stable. But what happens if I increase just 1 millisecond? Now let me use 557 milliseconds. Oh, the system is unstable. That is a nightmare. Let me tell you the following. 556 milliseconds. That is the critical clearing time. Critical clearing time is the maximum time that a fault can be clear and the system remain stable. And you can see, if I use here 556 milliseconds, let me use here because some of my students, they don't believe me. 556, run the simulation, 5 seconds. The system is stable. Of course, it's reaching this ugly angle over here. I don't like this angle. I don't like the system oscillating until 161 degrees. I don't like that. But the system stay stable. But if I put here, if the circuit breakers take so much time, like 557 milliseconds, wow, the system is unstable. If you remember, you can use the critical, you can calculate the critical clearing time using the equal area criteria. You can calculate the critical clearing angle using the equal area criterion. Here, because we are using time domain simulations, we calculate the critical clearing time. To be honest, if some of you go to the industry, to the transmission system operator, to any utility, the critical clearing angle is not useful. It's not useful because the angle is not a useful information for the basic protection system. From the protection point of view, time is the most important variable. Time is the most important variable because define the exposition of the equipment to the short circuit faults and so on. That is the reason that the critical clearing time is the important variable. And for this very basic system that I show you, the critical clearing time was 556 milliseconds, okay? Well, I highly suggest to do the following, okay? Here, right now, you have a tool to play games. To be honest, here you have the tool to learn many things. Of course, you need to have time to do that, okay? But if you run initial conditions, I highly suggest to do the following, okay? At home, when you have nothing to do, I highly suggest to insert here in the short circuit a resistor. If you include a fault resistant in the short circuit, you will realize that they have a very interesting impact on the critical clearing time, okay? I highly suggest that as exercise, okay? I highly suggest that you do that as exercise, okay? Okay, I will close this. Yes, this is so much for one day. Yeah, I am tired. At this moment, what I want to tell you is I am recording this session, I am recording this video, and I will upload later. I don't know if today, tomorrow, I don't know when I have time. I must run because I have one PhD thesis in 1 hour. I need to put my clothes, my elegant clothes, and so on. But I will be uploading this video, okay? If you fail to follow any step, I believe that you can go to the YouTube video, you can play backward, forward, etc., and you can reach all the steps, okay? I love those videos because you have the opportunity to learn at your own speed, okay? There are people that they learn extremely fast, probably they can jump the videos, but there are people that they require more support, okay? There are people that they need to watch those videos 2 times or 3 times or 10 times, I don't know. And that is it, okay? Well, any question at the moment?